Hello and welcome to the 7th lecture of this course. Today we will be talking about Quasi-Newton methods, especially the rank 1 method and DFP. Recall from the previous lecture, the Newton's method for minimizing a nonlinear unconstrained problem. The motivation for Newton's method came from the second order Taylor series approximation, which is f of xk plus delta k transpose gradient of f of xk plus half delta k transpose Hessian of f at the current point delta k, and if we try to minimize this approximation over all possible delta, we can get the best possible delta which satisfies this equation, gk delta equal to minus of gk. And if capital G is invertible, then delta is gk inverse gk. So the algorithm for Newton's method is while not converged, let delta k be the solution to gk delta equal to minus of gk, and the next iterate is just the old iterate plus the delta k and k equal to k plus 1. What we learned last time was this is fast, but does not always converge, even for the case when the Hessians are always positive definite, and the step number 1 requires inverting a matrix or solving a system of equations. Both are equivalent things, which is expensive. So order of n cube steps. So there are some methods where you can modify the search direction and do some line search, or modify this gk slightly and try to find the next solution. Those were discussed briefly last time, but today we will talk about Quasi-Newton methods which try to they try to guess GK inverse. And do a line search. These methods are practically much faster and more robust than the Newton's method. And it is a family of methods. It's not just one single method that we are going to see. There are many variants of these methods, and they have some nice rich theory around them. So before starting Quasi-Newton methods, let's look at some notation that we will use in this for these methods. So as earlier, GK is the Hessian of F in kth iteration. That means at xk, GK is the gradient of F. These we have been using for some time. Delta K is new here. Delta K is the change in X after the kth iteration. So this is xk plus 1 minus xk, and not xk minus 1. So it is important that delta k is the change from xk to the next iterate, not the previous one. Similarly, gamma k is going to be the change in the gradients from the current gradient to the next one. Okay, so lot of updates and point selections will use these symbols and not much of F and X and their gradients and Hessians. Okay, so so let's write the program outline. So the scheme of these methods is as follows. So instead of replace delta k equal to gk inverse times delta gk by first find a direction sk equal to minus of hk gk. So we will come shortly to what this hk is. This is a matrix n cross n. Then do a line search. So alpha k comes from the line search along Sk and the other change is that instead of moving by delta, now we don't have delta in these methods, we have xk plus 1 is equal to xk plus alpha k sk, and lastly hk plus 1, the new h, is going to be the old h plus something something, depending on the variant or the method. Okay, like I said that there are many variants of Quasi-Newton methods. So depending on which method we are talking about, this update will keep changing. And lastly, k is k plus 1. So by comparison to Newton's method, if I want, so this line search actually ensures global convergence, and this overcomes the problem of Newton's method, but at the same time recall that we are not using minus of gk like we do in steepest descent, but we are modifying the steepest descent direction by this matrix hk, and hk is a model or an approximation for the inverse of the Hessian. And this is done for speed. Okay, because we know that by looking at the Hessian, the Newton methods, whenever it converges quadratically. So using this, this Hessian inverse is a good idea, but we should not directly use it because one, it is difficult to compute the inverse of this big matrix, and second, this may not give us a descent direction if we just take gk inverse. Okay, so for the method to work, hk and hk plus 1 and so on and so forth should be positive definite. Why? Because my search direction, so if I do gk times sk, now if hk is positive definite, then this whole thing would be less than 0, and which implies that sk descent direction. Okay, so this point is important, that hk should be positive definite. And second, like we mentioned earlier, that hk should be nearly or as close as possible to gk inverse ideally. But what we do in these methods is actually we try to keep hk closer to gk plus 1 inverse. Okay, and the reason is that after every iteration the s and the alpha are chosen after h. So once I have chosen h, then only then in the next step I do a line search along s and find alpha and s. So if I want to choose hk, this would rather be closer to gk plus 1 and not gk. Okay, so I would like you to think about this a little bit more and read the explanation in the book to convince yourself that this makes a little bit more sense than being exactly equal to gk. And also we want to make sure that hk plus 1 and hk are not too different because of the reason number 2, and also because hk plus 1 has to be a simple update plus something, and this something should be simple enough. Ideally we want to do it in less than order n cube, okay, to keep it fast. Okay, so something like n square number of operations would be acceptable. Okay, so let's try to see what this h could be. Okay, so remember that we are trying to design an algorithm, so we would like to come up with some rules of creating h based on which then s and alpha can be decided. Okay, so what could h be? Okay, so h has to be positive definite. It should not be too different from the previous h, and as far as possible it should try to mimic the Hessian inverse.